Hello. In this video, we are going to discuss Latimer diagrams, specifically the Latimer diagram for sulfur. In a Latimer diagram, as we travel to the right, each of these individual steps refers to a reduction. So here we have sulfate being reduced to dithionate ion, and the cell potential for this standard reduction potential is minus 0.25 volts. So all our values here are in terms of volts. The first reduction that we are going to look at in detail and balance is the reduction of sulfate to dithionate ion. In the Latimer diagram, we have sulfate ion to the left, then we have the arrow, and then on the right hand side we have the dithionate ion. This tells us that there is a reduction reaction going on that reduces sulfate to dithionate, and that the standard cell potential for this is going to be negative 0.25 volts. To get the complete reaction, we have to balance, which is left out of the Latimer diagram for the sake of brevity. A first thing to notice is that in the sulfate ion, the oxidation number of sulfur isn't immediately obvious. We can assume that in anything other than a peroxide, that the oxidation number of oxygen is going to be minus 2, as long as it's not peroxide or elemental oxygen, for example. So each of the oxygen atoms has a oxidation number of minus 2. So that gives us a total of minus 8 for all the oxygens counted together. When we add the oxidation numbers together for an ion, the sum of the oxidation numbers has to equal the charge on the ion. So if we add up the minus 2 oxidation numbers for each of the oxygens to minus 8, plus the value for sulfur, this has to equal minus 2. The only way that is possible is if the oxidation number of sulfur is plus 6. And this is the highest common oxidation number of sulfur. And we notice that we double check, if we add 6 plus minus 8, we get a value of minus 2. On the other hand, in dithionate ion, we have 6 oxygen atoms, each of which has an oxidation number of minus 2. So that gives us minus 12 for all the oxygens taken together. Since the sum of everything has to equal minus 2, the only way that is possible is if the sulfurs altogether count as positive 10, because 10 minus 12 equals minus 2. And since the two sulfurs together count as 10, we can count each of them as plus 5. So one of the important features of this reaction is that sulfur goes from an oxidation number of plus 6 to an oxidation number of plus 5. It is reduced, which is what we expect. We know from Dalton's atomic theory that we cannot change one type of atom into another type of atom. At least in chemistry we can't do that. So we notice on the left-hand side of our reaction we have one sulfur atom, and on the right-hand side we have 2. Just as we can't create atoms out of thin air, we can't destroy them either. So this sulfur atom must have come from the left-hand side. So it must have come from a sulfate. So when we balance the reaction, we need to put a coefficient of 2 in front of the sulfate. Remember, when we're balancing equations, we can't change the identities of our particular ions, but we can change the coefficients in front of them. So this gives us 2 sulfur atoms on the left-hand side and 2 sulfur atoms on the right-hand side. We also notice that the number of oxygens is not balanced. But let's do something else first, based upon the fact that we know that the oxidation number of sulfur goes from 6 to 5. If we were to do this for one sulfur atom, to go from plus 6 to plus 5 would require 1 electron. Since we're doing it for 2 sulfur atoms, it must require 2 electrons. So an important part of our reduction reaction here is to write explicitly how many electrons are involved. And it's going to be 2 electrons in this particular case. We notice that we go from 8 electrons on the left, 8 oxygens on the left-hand side to 6 oxygens on the right-hand side. So we need to put 2 more oxygen atoms on the right-hand side. And the way that we do this is we presume that the additional oxygen came from water. So to get 2 additional oxygen atoms, we need 2 molecules of water, which we'll write as 2H2. Oh. So now, by adding water to the right-hand side, and since these reactions take place in aqueous solution, using water in this matter is entirely reasonable. We balance the number of sulfur atoms, we've balanced the oxidation numbers of sulfur itself, and we've balanced the number of oxygen atoms. We only have one thing left to do, and that is to make sure that the number of hydrogen atoms on each side balances. We notice that we have 4 hydrogen atoms on the right-hand side, so we need 4 hydrogens involved on the left-hand side, and we incorporate them as hydrogen ion. And we'll see in a second why this is an entirely reasonable way to introduce them, particularly because we're looking at a reaction that takes place in acid solution. When we have reactions that take place in acid solution, by the definition of an areneous acid, we're going to have H plus present. We know that under neutral conditions in aqueous solution that we have a concentration of H plus ion of 10 to the minus 7 molar. Okay. Are there any more things we have to make sure of? Yes, we have one final thing to make sure everything is okay. In addition to making sure that the numbers of atoms on each side is identical and that we made the appropriate changes in the oxidation number by adding electrons, we must also make sure that the charge on the left-hand side is equal to the charge on the right-hand side. Electrons are fermions, and we cannot create or destroy fermions. So therefore, we have to make sure that the number of fermions on the left-hand side equals the number of fermions on the right-hand side. And the way we do that is to make sure that the charge is balanced. We notice the easiest charge to figure out is on the right-hand side, since we have a neutral molecule and a -2 ion. So the charge on the right-hand side is -2. On the left-hand side, we notice that we have 2 -2s here, so that's -4, which exactly cancels the +4 of the hydrogen atom plus 2 electrons, which gives us a -2 charge on the left-hand side. Therefore, this is the complete and balanced reduction reaction for the first step that we saw in the Latimer diagram for sulfur in acid solution. The second step that we are going to look at is the reduction of dithionate ion to sulfur dioxide, which is a gas. In the next step of the Latimer diagram for sulfur in acidic solution, we have the reduction of dithionate ion to sulfur dioxide, which is a neutral molecule and is a gas at room temperature. Again, we want to figure out the oxidation numbers of sulfur in each case, and we saw in the previous reaction that in dithionate ion, the oxidation number of sulfur is +5. On the other hand, in sulfur dioxide, we know that each oxygen has an oxidation number of -2. Since it's a neutral compound, the overall oxidation number must be equal to 0. The only way this is possible is if the oxidation number of sulfur is +4. We notice again that we want to balance the number of sulfur atoms on each side, and we have 2 on the left-hand side, but we only have 1 on the right-hand side. And we remedy that by putting a coefficient of 2 in front of the sulfur dioxide, so that now the number of sulfur atoms on each side balances. We next want to look at the oxidation numbers, and we see that sulfur goes from +5 to +4, so that requires 1 electron for each of the sulfur atoms involved, and there are 2 atoms, so that means that we need 2 electrons to be transferred to achieve this change in oxidation numbers. So there we have our 2 electrons. We notice that on the left-hand side we have 6 oxygens, but we only have 4 oxygens, 2 times 2 equals 4, on the right-hand side. So therefore, we need to add 2 more oxygens to the right-hand side. And typically how we do this is consider that those oxygen atoms came in molecules of water. So for 2 atoms of oxygen, we need 2 molecules of good old H2O. And now the number of oxygen atoms on each side balances. We balanced the sulfur, we balanced the oxygen, we balanced the oxidation number on sulfur, which is a critical feature of oxidation reduction reactions that you must make sure that you've done. So the final step is to make sure that the number of hydrogens on each side balances. We see that on the right-hand side we have 4 hydrogens, but we have none on the left. So the way that we account for that is we put 4 hydrogens as H plus on the left-hand side. If we have done this correctly, the charges on each side should balance. If we check each side and the charges do not balance, it means that we made a mistake. We got to go back and figure out what we did wrong. So on the right-hand side, you have 2 neutral molecules, so the charge is 0. So that means that the charge on the left-hand side better be 0 or we messed up. But we have -2, another -2 is -4, plus 4 gives us 0. So we have charge of 0 on the left, charge of 0 on the right, which means that we have successfully balanced this reduction reaction. The third reduction that we are going to look at is the reduction from sulfate directly to sulfur dioxide in a single step. Now we look at the step in the Latimer diagram where we go directly from sulfate ion and reduce it directly to sulfur dioxide gas. We've already seen that in sulfate ion, the oxidation number of sulfur is +6, and that in sulfur dioxide, the oxidation number is +4. Notice here, we only have 1 sulfur atom on each side, which makes things at least a little bit different, a little easier. So to go from +6 to +4 for 1 atom, or 1 ion if you want to say it that way, requires 2 electrons, so we need 2 electrons. We notice on the left-hand side that we had 4 oxygen atoms. On the right-hand side, we only have 2. So therefore, we need 2 more oxygen atoms on the right-hand side. And the way that we do this is to add 2 molecules of water to the right-hand side, which is legitimate because we know that the reaction is taking place in aqueous solution. Or at least can take place in aqueous solution. Last but not least, we know that we have 4 hydrogens we have to account for, and we account for them in acidic solution by introducing them as H+, as a proton. And if we do this, we know that on the left-hand side, the overall charge now is 0. The right-hand charge is 0. And we have the balanced reaction for the direct reduction of sulfate to sulfur dioxide in acidic solution. The fourth step we're going to look at is the reduction of sulfur dioxide to tetrathionate ion. The next reduction reaction that we're going to look at is the reduction of sulfur dioxide to tetrathionate ion in acidic solution. And this one features lots of complications, so it's a very interesting and tricky example. The first thing we should probably do is notice that we only have 1 sulfur on the left-hand side, but we have 4 on the right-hand side. So immediately we need to introduce the coefficient 4 on the left-hand side to account for the numbers of sulfurs on each side, to balance that out. Next, as has been our wont, let's look at the oxidation number of sulfur. In the case of sulfur dioxide, we've already seen that the oxidation number is +4. And we're going to run into a problem when we're doing it for tetrathionate ion. So let's see what we get. Each of the oxygens is -2. So all the oxygens together account for a -12. We know that the sum has to equal -2 for an ion. The sum of the oxidation numbers equals the total charge on the polyatomic ion. That means the 4 sulfurs together must account for +10, because +10 minus 12 equals minus 2. This is a little tricky because we have to account for the oxidation numbers of sulfur, each being 2.5, which is not normally how we think about it. Or we can think that two of the sulfurs have an oxidation number of plus 2, and two have an oxidation number of 3. Either of those solutions will work out. Let's try, for this, even though it seems a little tricky, let's think about it as having an oxidation number of plus 2.5 for each one. Since we're going to be accounting for 4 sulfurs at a time, rather than each individual sulfur, this shouldn't introduce too much difficulty once you kind of get the hang of it. Okay, so here we have 4 sulfurs that each have an oxidation number of plus 4, going to 4 that have an oxidation number of 2.5. So 4 4s here accounts for plus 16. Over here we have 4 times 2.5 equals 10. So to go from plus 16 to plus 10, we have to add 6 electrons. You have to subtract 6. So the way that we do that is we add 6 electrons. So this is a tricky part to see. We'll see later on another way we could have gotten to the same answer without having to worry about whether we counted the sulfurs in tetrathionate as being 2.5 or half of them being 2 and half of them being 3. So we'll show another way that would give us the same answer. But anyway, this is consistent with the way that we've been doing it so far. As far as oxygen goes, we have 8, 4 times 2 oxygens on the left-hand side, but we'll only have 6 on the right-hand side, which means that we have to, again, add 2 more oxygen atoms, which means 2 more molecules of water on the right-hand side to balance the number of oxygen atoms. And with that in mind, we have 4 hydrogens that we have to now introduce to the left-hand side. And we introduce them as H+, the proton, because we're doing it in acidic solution. As our final check, we notice that on the left-hand side, this is a neutral molecule. So we have minus 6 plus 4 is a minus 2 charge. On the right-hand side, we have a minus 2 charge as well. So therefore, the charge is balanced. And we have good confidence that we have successfully and accurately written down and balanced this reduction reaction. So now, suppose we were confused about the 6 electrons as far as the oxidation numbers. What we could have done is to have proceeded ignoring the oxidation numbers entirely, and notice that based upon the number of oxygen atoms, we had to introduce 2 molecules of water, and then that we had to introduce, on this side, 4 protons, 4 H+. If we had left it at that and ignored the number of electrons, the charges on each side would have been balanced. And the only way to have balanced the charges would have been to introduce 6 electrons on the left-hand side. So if we were confused about how many electrons we needed, the only way this will balance is if we have 6 electrons on the left-hand side. So thank you very much for your attention for this particular step, which is a tricky step at that. Next, we are going to look at the reduction of tetrathionate ion to thiosulfate. In our next reaction, we're looking at the reduction of tetrathionate ion to thiosulfate in acidic solution, which our Latimer diagram tells us has a standard reduction potential of 0.07 volts. So we'll proceed as we had before. We know that we have to balance the number of sulfur atoms on each side. And we notice that we have 2 on the right-hand side, 4 on the left, so that we require a coefficient of 2. As far as oxidation numbers, we recall from what we just worked on that the oxidation number in tetrathionate ion has the strange but useful value of 2.5. In the case of thiosulfate, each of the oxygens has a minus 2 charge, minus 2 oxidation number. So all the oxygens together count as minus 6. The overall oxidation number is minus 2. The only way this is possible is if all the sulfurs together have a total oxidation of plus 4. Since there's 2 atoms, that means that each one must be plus 2. And notice that as we proceed from left to right, since we're doing reduction, the magnitude, the positive magnitude of the oxidation number on sulfur keeps decreasing. If you find that it doesn't decrease and you have a legitimate Latimer diagram, then you're clearly making mistakes somewhere. So because each step is a reduction, we're going to have a reduction, as it works out, pun intended, in the oxidation number on sulfur in the sulfur Latimer diagram, or the atom in important respective atom for the particular Latimer diagram that you're looking at. Okay, so we have on the left-hand side, we see that we have 6 oxygen atoms, and on the right-hand side, we have 6 oxygen atoms. So we're good oxygen atom-wise. We don't have to introduce any molecules of water at all in this case. So that's good. So, but we do have to introduce electrons because we're reducing tetrathionate ion. So the 4 sulfurs together count as plus 10, whereas the 4 sulfurs together here, each of them counts as plus 2. There's 4 of them, so this is plus 8. So we're going from plus 10 to plus 8, and the only way this is possible is if we introduce 2 electrons. So we need to add 2 electrons in this particular reduction. So let me repeat what I did, because that may seem a little tricky. So we have the oxidation number for each sulfur. We multiply that together to get the total oxidation value for all the sulfurs together. So 4 times 2.5 equals 10. Over here, now notice each of the sulfurs is plus 2. And we have 4 of them because we have 2 molecules, each of which has 2. So make sure you count all 4 sulfurs here. Multiply it by 2 to get 8. So we go from 10 to 8. The only way that's possible is with 2 electrons. We notice that on the left-hand side, the charge is now minus 4. But the charge on the right-hand side is minus 4. So we're all good. In our next reaction, we are going to look at the reduction of thiosulfate ion in acid to sulfur. And we notice that the reduction potential here has a greater positive value than the reduction potential to the left. This tells us that in acid solution, thiosulfate is unstable to disproportionation. And we'll see exactly how we can evaluate that using the Latimer diagram. Recall that we found the oxidation number of sulfur in thiosulfate to be plus 2. The oxidation number of sulfur in elemental sulfur, which we're just writing as S here, sometimes you'll see it written as S8, is 0 because we recall that one of our rules for oxidation number is that the oxidation number for any element as an element is going to be 0. So we realize that to go from an oxidation number of plus 2 to 0 requires 2 electrons. But we have to remember that we have not just 1, but we have 2 sulfur atoms. So first, let's balance the number of sulfur atoms we have, because we need to do that in any case. And then we realize that we need 2 electrons for each sulfur atom, so we're going to need a total of 4 sulfur atoms to reduce the sulfur in thiosulfate to elemental sulfur. So we put in our 4 electrons here. Now we notice that on the left-hand side, we have 3 oxygen atoms. So to balance the number of oxygen atoms, we do our procedure that we've used before, and we add the same number of molecules of water, which is 3 here. So we need 3 H2Os. This makes sense, of course, because these reactions are considered to take place in aqueous solution, our most common solvent. So now the oxygens and sulfur atoms on each side balance. The oxidation numbers are properly arranged. But now we have 6 hydrogens on the right-hand side, and we have none on the left-hand side. So we do our final step, which is to add 6 protons, 6 H pluses, on the left-hand side, which will balance the number of hydrogens. This makes sense, of course, also because these reactions are taking place in acidic solutions. So we're looking at the Latimer diagram in the case of acidic solution. So our final check is to make sure that the charge is properly balanced. So on the right-hand side, we have 2 compounds, or a compound and an element. So those are both neutral. So the overall charge on the right-hand side is 0. On the left-hand side, the charge is minus 2 minus 4, that's minus 6, plus 6. So we have a charge of 0 on the left-hand side as well. Therefore, we have properly balanced the reduction of thiosulfate to elemental sulfur. Recall in a previous step that we had worked out the reduction of tetrathionate ion to thiosulfate. And recall that the listed standard reduction potential for this reaction is 0.07 volts. So here we have a species that in our Latimer diagram, coming from the left, we have a voltage of 0.07, and then going to the right is 0.60 volts, and 0.60 volts is greater than 0.07. It's a more positive value. Whenever we see this situation, we predict a certain phenomenon is going to occur. This phenomenon is called disproportionation. Disproportionation is a phenomenon where we have simultaneous oxidation and reduction of the same element. In this case, we're going to see simultaneous oxidation and reduction of the sulfur in thiosulfate in acidic solution. In biochemistry, the same phenomenon goes by a different name, dismutation. So dismutation is just the biologist's way of saying disproportionation. By far the most important case of dismutation is the dismutation of oxygen and hydrogen peroxide, going from an oxidation number of -1 to -2 in oxide and to 0 in elemental oxygen. There are two important enzymes which are involved in this process. The first is called superoxide dismutase, and the second one is called catalase. So whenever you hear dismutation, it means exactly the same thing as disproportionation. We now want to write out what the net effect of the disproportionation of thiosulfate is going to be using the two standard reduction potential equations that we have already worked out. So the first thing we want to do is to flip this reaction. So we want to switch the products and the reactants, and when we do such a process, even for standard reduction potentials, the effect is to change the reduction potential's sign. So it's going to go from positive to negative, negative to positive. We can think of it as toggling the sign or flipping the sign. This is very much in keeping with the procedure that we would perform if we were handling the enthalpy, the entropy, or the Gibbs free energy of a thermochemical equation. So what we're going to do by the miracle of editing is to flip the reactants and products and at the same time change the sign of the standard reduction potential. Voila, the reaction has been flipped. So now the former reactants are now the products, and the former products are now the reactants. And in the process, we've flipped the sign of the standard reduction potential, and we've highlighted the negative sign by putting it in purple. We have one more step we need to undertake before we can find the net result of the combination of these two reactions. We want to have it such that when we add the two reactions together, there is no net gain or loss of electrons. So rather than having essentially a half cell potential, we want to write it as if it were a complete circuit where we have no gain or loss of electrons. So to do that, we need to multiply the second reaction through by a 2. So we need to multiply each coefficient by 2. And let's see what we get when we do that. So first we multiply 2 times 2, we get 4 here. We need to multiply the implied 1 coefficient here by 2, and then the coefficient of 2 for the number of electrons. Kind of erases entirely just to make it a little neater. So we have 4 electrons there. So now notice that we have 4 electrons on the left-hand side and 4 electrons on the right-hand side. So how do we alter the standard cell potential when we multiply through by a constant? Now here's a big difference between the standard cell potentials and the enthalpy, for example, in that if we multiply through by a constant, we do not change the voltage. So an impressive experiment that is often done as a demo is to take a battery, measure its voltage, and then to chop the battery in half. And one sees that when you chop a battery in half, it does not change the voltage. So the voltage is an intensive property, not an extensive property. So remember, the voltage is the joules per coulomb. So it's intensive because it's two extensive properties that are taken as a ratio. Anyway, so the important thing to remember is when you're handling cell potentials and you multiply through by a constant, do not multiply this through by the same constant. Now we are free to add the two reactions just as we would in a Hess's law problem. So on the left-hand side we have 5 thiosulfates, S2O3. Two minus. And notice that since we have the same number of electrons on the reactant side and the product side, these cancel out, so we kind of show our cancellation. Plus 6 hydrogens. Then on the right-hand side, we have our 2 molecules of sulfur, or 2 sulfur atoms, if you want to put it that way. Plus, we have 2 tetrathionate ions. Plus 3 molecules of water. So this is the net disproportionation reaction for thiosulfate in acidic solution. So we see that on the left-hand side, just to confirm this, recall that the oxidation number of sulfur in thiosulfate is +2. The oxidation number of sulfur in elemental sulfur is 0. And that the oxidation number of sulfur in tetrathionate ion is going to be 2.5. So we see that some of the sulfur in the thiosulfate, 2 of those, are reduced from +2 to 0, whereas 8 of them are going to be oxidized from +2 to +2.5. So here we actually see the simultaneous oxidation and reduction of one element, which is sulfur. Now we can figure out the overall cell potential of this reaction in acidic solution by adding the two values up here. So we have 0.60 volts and negative 0.07. So that gives us a value of plus 0.53 volts. And since this is a complete cell reaction, not just a half reaction, we can interpret the positive value the following way. It tells us that this particular reaction is going to be spontaneous under standard conditions, which is part of the reason why we have this rule, heuristic rule, in Latimer diagrams, that if the value, the voltage to the right, is greater than the value to the left, that we're going to have disproportionation. This is the value to the left, which becomes negative. So since this value is greater than this value was before it was negative, that means that when we subtract the two, we end up getting a positive value. And since it's positive, it is spontaneous. For our last step, we're going to look at the reduction of elemental sulfur to hydrogen sulfide gas. The last reaction that we're going to look at for this particular Latimer diagram is going to be the reduction of elemental sulfur to hydrogen sulfide, which is a foul-smelling gas. In sulfur, as an element, the oxidation number, of course, is 0, because that's true for any element. In case of hydrogen sulfide, recall that hydrogen will generally have an oxidation number of +1, unless it's in the very special compounds which we call hydrides, or if hydrogen is an element, in which case the oxidation number would 0. It's -1 in hydrides, but typically it's going to be overwhelmingly +1 in compounds. So since the hydrogens are each +1, the only way this is possible is if the oxidation number of sulfur is -2. So -2 plus 1 plus 1 gives us a total oxidation number of 0, which is required for a neutral compound. So how do we account for this? Well, we notice that to go from a 0 oxidation number to a -2, we require the addition of 2 electrons. So that balances the oxidation numbers on sulfur, which undergoes the redox reaction. And we know that we have two hydrogen atoms on the left-hand side, on the right-hand side. So typically we have hydrogen appears in molecules of water, but here we have it in a molecule of hydrogen sulfide. But we treat it the same way as we would water. We introduce it because we're in acid solution as coming in from H+. And if we do this, we notice that on the right-hand side, the total charge is 0. On the left-hand side, the total charge is 0. So therefore, we have successfully balanced the redox reaction going from elemental sulfur to hydrogen sulfide. I thank you very, very much for your attention. As always, this was a very long video, and I appreciate your attention during the details of it. Have a good one.